There we go. All right, so again, guys, the topic today is subatomic particles and atomic structure, and I'll make the connections for you in a second, but this is what we're going to accomplish today. First thing we're going to do is we're going to talk about where atoms come from. Kind of sounds like where do babies come from, but it's a completely different conversation. So where do atoms come from? Then we're going to talk about how big are atoms. And I'll be honest with you, this gets a little bit ridiculous. But guys, the ridiculousness of it is actually necessary because atoms are ridiculously small. And then guys, we're going to wrap up the day by grabbing our periodic tables and talking about what atoms are made of. I think you probably know protons, neutrons, and electrons, but we're going to talk about how many are in each atom, and then we're going to grab a hold of some homework, and you'll probably get done with your homework today. You guys ready to dig in? Here we go. So guys, last time in class, we had this conversation, right? And we talked about the triangle. And we took this thing and we tore it apart, and we talked about the two types of matter, which were homo and heterogeneous. And we found out that heterogeneous things have to be mixtures. And we found out that these things can be separated by physical means, which was our first question in our chart. And then we talked about homogeneous, which is the same thing the whole way through. And we said that there are two kinds of homogeneous things. There are homogeneous mixtures that we call solutions, but remember, they are not unique. They look like and taste like and feel like and behave like the things that make them up. And then there are substances, and substances are unique. They have unique physical and chemical properties. That was the lab that we did on Friday. And then, guys, we said that there are two kinds of things that are unique: elements and compounds. Is it all coming back to you? Okay, so guys, what we're going to do today, I kind of like it. Here he comes. Guys, what we're going to do today is what we're going to do for the rest of the unit. Guys, the rest of this unit, and actually, this is crazy, the rest of this unit, the whole next unit, and the whole unit after that are all about elements. So guys, what we're going to do today and Thursday is talk about the fundamentals of elements. Then guys, when we get back together in the unit after that, we're going to talk about the nucleus of atoms. And we're going to grab things like uranium, and we're going to talk about what things like uranium do when they break apart and they break down, and we call that radioactivity. And we're going to spend an entire unit and we're going to talk about that. And then the unit after that, we're going to figure out what the electrons are doing, and we're going to start drawing things that look like this when we find out that this is actually more like what electrons are doing, and they don't actually look like planets going around the sun. So guys, as we get into what we're doing today, understand that we're really setting the stage for basically the next month and a half, because the next two units after this are all about elements as well. So you guys ready to make the transition? Grab your notes paper. Here we go. So guys, what we're going to do first is we're going to talk about where atoms come from, and I would write down the subtitle right here. We're going to talk about atomic evolution. Now guys, as you're writing this down, here's the disclaimer. I am not pushing an agenda with you when we talk about evolution, okay? You can embrace what we're about to talk about as an evolutionist. You can embrace what we're about to talk about as a creationist. It doesn't matter how you understand this. Understand the facts are the facts. But then once you get beyond those and you figure out how this came together, guys, that's completely up to you. And you know that I come from a faith tradition like many of you do. It's different, but it's similar in importance. And guys, understand, I'm completely at peace with what I'm about to share with you. So I'm not challenging your faith. I'm not challenging your understandings of the universe. Guys, bottom line is this: whether this happened because God is smart, or whether this happened because the universe just happened to work out this way, that's completely up to you. However you choose to make sense of this, this is what we know as scientists. And I'm going to share with you the facts. You can ask the bigger questions over in seminary. So guys, it goes like this. These are the questions that we're going to ask and answer, and I would encourage you to write them down. Skip 2 spaces between each one. So guys, the first thing we're going to talk about is this, and this is all going to be on the test next week. Where did all the hydrogen in the universe come from? Some of you have the misconception that water is the most plentiful substance around, and it is on Earth, but it's not in the universe. Guys, the universe is primarily made of hydrogen, which is the lightest, simplest element in the universe. The question is, where did it all come from? Then, guys, we're going to talk about stars. You'll understand why in just a minute. Then we're going to ask this question. What is the heaviest element that a star can produce? Then we're going to answer this question. Where did the elements heavier than iron come from? And then, guys, we're going to wrap up with this question. What is the heaviest element, naturally occurring element in the universe? This is your second year, right? Okay. So you weren't there when Neil deGrasse Tyson came and did the devotional, right? Were you there? I think you were. He did it at BYU. Okay, so I think you were still here. It might have been your senior year. Okay. Were you there? No, you're not. Are you at UVU or BYU? Were you there when Tyson did the devotional at BYU? Okay. You guys are going, first of all, who am I talking to? Because, Gracie, I should have you introduce Jessica. Apparently you know one another. It was a beautiful moment. So guys, this is Jessica Reese, who was a student of mine a couple of years ago, and she's trying to figure out what she wants to be when she grows up. So she's going to hang out with us for a little while. And then we will always have, are you 276ing, or what are you doing? No, okay, so this is something different. We'll always have students from the local universities in and out of our classroom just sort of watching what we do. So anyway, we're surrounded by college students. It's kind of frightening. So guys, here's what we're going to do. And you'll see, I've embedded videos throughout this day, because frankly these videos do a great job of explaining what we're talking about. So guys, what you're going to see is all the answers to these questions are in the video. Please don't try to write down the answers. We'll come back and talk about them. But here's the bottom line. So what you're going to see when I start this video is there's going to be like this ethereal blue cloud. And guys, that ethereal blue cloud is meant to represent our early universe, when the universe was just hydrogen spreading out. We'll talk more later, but after the Big Bang. Then what you're going to find out is, well, Neil deGrasse Tyson, if you don't know him, he's an enormous African-American astrophysicist at Caltech, and he's also a NOVA presenter. And this is actually a chunk of a NOVA video, but he's got a wonderful voice. You'll love him. And he actually, what we were talking about with the ladies is that he actually did a devotional at BYU. Normally they record the devotionals at BYU and then post them online, but they couldn't record this one because Tyson's contract with NOVA says that he can't do that. You can't, they basically own him. And so they couldn't record this because it would have violated his contract with PBS. I was really disappointed. I understand it was brilliant. But anyway, so guys, we're going to watch the video, then we'll come back and answer these questions. And at the end of this, you will be able to answer the question, where did the atoms come from? Then we're going to start talking about how big they are and what they're made of. So here we go. So guys, this is the universe shortly after the Big Bang. Come on, Neil, tell us about it.
As hydrogen piles on, the central region grows more and more dense until something brand new lights up the universe. A star. These first stars are hydrogen giants, 100 times or more larger than our own sun.
Did you guys know that? Listen to these next couple words. I'll go back.
These first
So these are the first stars in the universe that are forming after the Big Bang. But listen close to the words.
stars are hydrogen giants, 100 times or more larger than our own sun.
So he just mentioned the sun in the context of stars. Do you guys understand the connection? The sun is a star. Did you guys know this? Okay, so guys, if you didn't understand this, our friend Mr. Sun is a star. Just like when you look out into the starry night and you can see stars, our sun is a star. So if there is alien life in other galaxies, they could look back at us and see our sun, and it would look like just like any other star. So in theory, there could be intelligent life in other places that look at our sun and go, twinkle, twinkle, little star. Because guys, our sun is a star just like all the batrillions of stars all throughout the universe. Yes, batrillion is a number.
Such massive stars are short-lived, 2 or 3 million years at the most, and they go out with a bang. In explosions so big, they've been dubbed hypernovae. And it's with these cataclysms that the universe begins to accumulate the building blocks of life. All the atoms in the universe heavier than hydrogen and helium are forged by stars.
Stars are really interesting. They don't just sit there. You know, because they last so much longer than we do, we think they're permanent.
Stars are the ultimate alchemists. They turn light elements into heavier ones. They get the energy that they need to glow that way. The star begins its life made out of hydrogen and helium mostly, about 70% hydrogen, 28% helium in the case of the sun.
In a star's core, the temperature and pressure are so high that hydrogen atoms fuse together to make helium. Hydrogen fusion releases prodigious amounts of energy, the heat and light of a star.
That's the story for 90% of the life of a star, fusing hydrogen to make helium.
Eventually, though, the star runs out of hydrogen and begins to fuse its stocks of helium, making yet heavier elements.
And so the way it works, and it always works this way, is that it contracts and it gets hotter. And if it can find something new to burn, whether it's the kitchen sink or coal or whatever, it'll burn it.
Helium is taken 3 at a time to make carbon.
You can add one more helium to that carbon and make element number 8, oxygen.
That's a tremendous step forward. You get carbon and nitrogen and oxygen made in stars.
Now this is great because on the board we already have the principal elements of life.
Organic chemistry is the chemistry of carbon.
Carbon fuses next, and still heavier elements begin to form.
Sulfur, argon, chlorine.
Potassium, calcium, scandium. The pace of this gets faster and faster.
Back in the middle, silicon is starting to burn at 3.5 billion degrees, stupendous temperature.
It makes titanium, vanadium, chromium,
manganese, cobalt, nickel, and iron.
Iron is really the end of the road. It's sort of the nuclear turnip out of which you just cannot squeeze anymore.
It's the end of the game. A star that has relied on fusion has come to the point where it has nothing more to spin.
The star is suddenly caught in a disaster. There's radiation going out from the outside, but deep in the inside, there's no more fuel.
Iron can't fuel this stellar furnace, and so, when a star builds up too much iron, it dies.
The core collapses, it bounces.
And it begins to move out, first slowly and then faster and faster.
And that sends a very sharp wave back out through the star.
And now what was falling down is going out, the whole thing's blowing up. And you've made a supernova.
A supernova explosion can be as bright as 4 billion stars like the sun.
A stupendous explosion.
Such outrageous energies overcome the iron barrier, cooking atoms into all the rest of the elements on the periodic table.
So starting down here, You can go copper,
zinc,
gallium,
germanium,
arsenic,
zirconium, niobium, molybdenum, technetium,
strontium,
rhodium,
lutetium,
antimony,
ytterbium,
tellurium,
thorium,
iodine,
radon,
xenon, cesium,
francium,
barium, lanthanum,
tellurium,
cerium,
indium,
actinium,
xenon,
thorium, protactinium,
cesium.
uranium. Done. That's enough elements.
We are all stardust. The carbon in our bodies, the iron in our blood, the calcium in our bones. Every last atom was formed in a star.
All right, guys, there you have it. You ready to talk about it? Okay, so it goes like this. Do any of you know the current estimate on the age of the universe? Do you know? Do you guys know? Not the solar system, the universe. Do you actually know? Is it? Go ahead. Billion. I think it's billion. I remember 11. I know the number's billion. So let's call that the number. We're still trying to figure it out. So guys, this is the way this goes down. You ready? You ready for 11 billion years of history in about the next 30 seconds? Goes like this. 11 billion years ago, what existed? And guys, the answer is the thing they call the singularity. And contained inside this thing called the singularity was the entire universe. Not the Earth, not the sun, not our solar system, not the Milky Way galaxy, but the entire universe was inside this thing called the singularity, and it was the size of a pinhead. Okay? So imagine the entire universe inside something the size of a pin. And then what did this thing do? It exploded. And guys, when something that small and that massive explodes, it's going to be big. We call it the Big Bang. And when that thing exploded, it started to expand. And as it expanded, it started to cool. And as it cools, we start to see atoms begin to form. And so guys, the story then, if I could find my laser, the story then goes like this. As the Big Bang expands and cools, it forms the elements hydrogen and helium. So all of the hydrogen, and these are questions, we'll go back and answer them. All the hydrogen and helium in the universe was actually formed in the Big Bang. So when you go down to Zurcher's and get yourself a helium balloon, the helium that's inside that balloon was formed 11 billion years ago in the Big Bang. Okay, so now you've got hydrogen and helium. And then what happens, guys, is hydrogen and helium, remember what we learned in the last unit, hydrogen and helium has mass. Therefore, it exhibits gravity. And these hydrogen and helium atoms start to attract other hydrogen and helium atoms. Their gravity kicks in, and they start clumping each other together. And as they clump together, more clumps together, and more clumps together, and more clumps together. And what do they start to form? Stars. And they become so big and so massive, and therefore so much gravity, that the gravity is so strong that not only do the atoms attract each other, they smush together and they form heavier and heavier elements. So they mentioned this in the video, that eventually things like 3 helium atoms stick together, and then you get carbon. And then another helium atom sticks to that, and you get oxygen. And in these stars, because they're so big and so massive and so hot, these atoms start to stick together, and they make heavier and heavier and heavier and heavier elements, until the point where even things like silicon start to bond together. And silicon is sand. And eventually, even these atoms start to stick together, and we keep getting heavier and heavier and heavier elements until the star gets to which element? Iron. Guys, iron is not fusible. The star cannot generate enough energy to get iron to stick to other atoms. And so eventually the star becomes a big bundle of iron, and it burns out. It's kind of like your propane grill running out of propane. It ain't got anything to burn anymore, and it flickers and it goes out. But the tricky bit is that as it flickers and goes out, what happens is the core of the star collapses. There's no longer the energy pushing out, and so the core collapses. And when it does, it bounces, and it sends a shock wave through that dead star, and that shock wave starts to move faster and faster and faster and faster and faster until it causes the star to blow up. And when the star blows up, what do we call it? Supernova. Go ahead, Brighton. Let's ask Siri. I guarantee she's going to get it wrong. How old is the sun?
Okay, check it out.
I hate you. Siri never gets this right, but now watch this. You go to Google. Oops. Google never misses. Watch. No, I wasn't. How old is the sun? Oh. 4.6 billion years. Never talk to Siri, always talk to Google. So 4.6 billion years. So our what's that? It will. Yeah. Don't buy insurance. It's not going to happen in your lifetime. But no, Brighton, you're absolutely right. This is the end game for the sun as well. Because our sun, like all these other stars, are turning hydrogen into helium into other elements. And eventually our sun is going to slow down, burn out, bounce, and explode. Absolutely. And so eventually the Earth is going to be consumed by the sun as it expands and blows up. Not this week, but eventually, yeah, this is going to happen. Yeah, go ahead.
But how are we able to say that? Like, all the stars in the universe can only get to iron light.
Yeah, it's a good question. And so I wish I could get into the physics of it, but there are constraints in terms of how big stars can be and how much heat they can produce as a result. And understand, not all stars are the same. There's probably 30 different sizes and temperatures of stars. Our sun is actually what is called a G2 class star. And so it goes A, B, C, D, E, F, G, I think it goes to like J. And then within that there are numbers. And so our sun is a G2 star, which frankly means it's ridiculously average. But there are stars that are bigger and cooler, interestingly, and then there are stars that are smaller and hotter, and there's a whole range of them. But typically, there are a few examples. Typically, they just can't get anything heavier than iron to go together. Go ahead, Cam. Yeah? Oh, it would be long over before that, because so what happens is the core collapses and then the star starts to expand, and it literally gets bigger. Before it explodes, it gets bigger, and that I don't know if this is a word, that biggering, as the sun gets bigger, it will consume the Earth and then it'll blow up. So it won't become a supernova till after it's consumed. I think it's the inner 5 planets. I forget quite how big it'll be. Well, but understand, fast on the scale of 11 billion years, it's like a flash in the pan. But we're still talking a million years. It happens over a long period of time. It's not like a weekend. But in the bigger cosmic sense, it happens in the blink of an eye. Yeah, go ahead. Go ahead. Okay. You don't. It's about this in the next unit. Your misunderstanding right now, which I can address, is that the initial bombs, atomic bombs, took heavy elements, uranium and plutonium primarily, and split them apart. And that releases energy. But the bombs that are the big issue now, this is the one that Kim Jong-un claims to have just detonated, which is causing all of these problems, is not a plutonium-uranium bomb, it's a hydrogen bomb. And in a hydrogen bomb, you're not splitting the atoms, you're fusing the atoms. And so literally what you're doing is creating a little sun. And so that's the big issue, because the amount of energy that's released when atoms fuse together is orders of magnitude bigger than when atoms break apart. And so, I mean, we've got thousands of hydrogen bombs, but they're called fusion bombs. We think North Korea just might have one as of the last couple weeks. But it's the opposite process. Instead of breaking, it's fusing, and that's what happens in the sun. Because you're right, you couldn't make a fusion or a fission bomb out of hydrogen because it can't break down anymore. It's the smallest atom. So, you guys, oh, go ahead.
Haven't scientists said that in the universe nothing can be created or destroyed, and the Big Bang theory is
Bless your heart. Okay, so there's a rule, right? It's the accounting of the universe that says matter can never be created or destroyed, right? It's called the law of conservation of mass. Guess what lab we're going to do on Monday? The law of conservation of mass. This is where we're headed next. You guys are awesome. So, yes, the law of conservation of mass says that matter can never be created or destroyed. But Einstein said that energy, E, is equal to mc squared. And so when we say that matter can never be created or destroyed, that's in chemical processes. But in nuclear processes, you can take energy, E, and convert it into matter, M. And so in nuclear processes, energy can become matter. And that's what happened in the Big Bang. The thing that banged was actually just a ball of energy. And when it expanded, that energy was converted into matter, which then formed hydrogen and helium. Yeah, but your question's great. You guys are good. You guys good? Okay, so where were we? Where did we get to? Iron, right? Iron, we good? Okay, so guys, iron, stars, make an iron, and then when the sun or the star gets to iron, what happens? Burns out, right? Gives up, done, right? Done. Can't go any further, runs out of fuel, if you will, and the core collapses, expands, it bounces, the star blows up, and again, what do we call it? Supernova. But guys, when that star explodes, now we're talking about energies that are completely unlike the energy of stars. And the energy of these supernova explosions overcome what we call the iron barrier, and now all of a sudden all of these elements heavier than iron, while iron starts fusing together with all these other elements and makes heavier and heavier and heavier elements up until uranium. And guys, that's as far as we get in the supernova. That is the heaviest element in the universe is uranium, because even the supernova aren't energetic enough to make elements heavier than that. So then guys, where do we get elements heavier than uranium? It's us. We make them. We actually go into lab and we take atoms and we shoot them at each other at near the speed of light. And if we can get them to hit, sometimes they stick. And if they stick, they make what we call the super heavy elements. You get the idea? Many times they do. Actually, it's really interesting. I can remind me if we have time at the end of class, and I'll show you pictures. Actually, many times they do. They hit, and when they explode, they'll actually follow the trails that come out of the explosion to see whether or not initially they did stick and then exploded. But many times they do. They'll just explode, which is why it takes sometimes decades to get just a couple of any individual atom, because many times they do hit and blow up. So, yeah. Okay, so guys, let's go back to the questions then, and let's talk about some answers. You should know these now, and you're just filling in the blanks because you already wrote down the question. So guys, where did all the hydrogen in the universe come from? Big Bang. This won't be on the test, but maybe a word that you're interested in is singularity. That's the thing that banged. We call it the singularity. If you want to really dig into some interesting stuff, and I'm not even going to entertain this, but I'm going to lay it out there, where did the singularity come from? You guys can think about that on your own. Then guys, question number 2, what are stars? What are they? What are they made of? Hydrogen and helium. They're big balls of hydrogen and helium, and the hydrogen and helium is fusing, you'll notice I underlined it, fusing together to make heavier elements. You guys okay? Question number 3. So guys, question number 3 said this: what is the heaviest element that stars can produce? And it's a simple answer. What is it? Iron. Good. Yep. So if that's the case, where do the elements heavier than iron come from? Supernova. Dying stars. And guys, we're not going to get into this, but strongly encourage you, if you go to college, take an astronomy course. Not all stars go supernova. Not all of them do. Other things can happen as well. But for what we need to know, supernova, when the star explodes. And then guys, what is the heaviest naturally occurring element? It's uranium. Yep. And again guys, anything heavier than uranium, we find that only in university research labs where we make it on our own. Okay, so in my brain we're done with question number 1. Where do atoms come from? Any questions or other things you want to explore with this? You guys groovy? Okay, so now guys, what we're going to do is we're going to answer question number 2. We now understand where atoms come from. Now the question is, how big are these things? And I think you guys are comfortable with the idea that they're small, right? But the question is, how small are atoms? And guys, we're going to get back into this and we're going to talk more, but I'm going to show you another video. Can I switch the page? You guys are okay? Okay, so guys, what I'm going to do is I'm going to show you what is called a TED Talk. If you're not familiar with TED, it's a symposium of technology, entertainment, and design. And basically what happened is about 10 years ago, this person, I forget his name, said, why don't we just get really intelligent people together, give them the stage for 10 minutes, and let them tell us their stories. And that's how TED got started. And they literally held him to the clock. I think it was like 9 minutes. But they said, hey, intelligent people, come together and in 9 minutes tell us the things that you're thinking about. They did this for a couple of years, started recording them, started posting them on the internet. A lot of them went viral. And then they ended up creating this website called TED, and you can now watch what are called TED Talks. So guys, this is actually a TED Talk where they ask a guy this question: how big are atoms? And so he and some animators, this guy's actually a nuclear physicist, he and some animators put together this video.
You probably already know.
Ooh, that's loud. This is actually kind of what this guy looks like. If you saw the entire TED video, you actually see him up on stage. But this is kind of what he looks like. So again, guys, the question that we're asking and answering is, how big are atoms?
Everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit?
Okay, do you understand the question? How many atoms are in a grapefruit? So grapefruit, like the size of a softball, citrus fruit, right? Can you picture a grapefruit? How many atoms are in a grapefruit?
Well, let's assume that the grapefruit is made up of only nitrogen atoms.
Okay, so now what he's saying is this: the grapefruit only contains nitrogen. That's not true. It's got other things in there as well, lots of other things. But just so we can do the math, we're going to say that a grapefruit is just a big ball of nitrogen atoms. So now, how many nitrogen atoms are in a grapefruit?
Which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry.
Got it? So now, guys, what we're doing is we're taking each of the atoms inside of a grapefruit and we're blowing them up to the size of a blueberry. Can you picture it like a marble? Okay, so every single one of those atoms we're going to blow up to the size of a blueberry. The question is this: how big does the grapefruit become?
And then how big would the grapefruit have to be? It would have to be the same size of, well, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit?
Got it? So guys, here's what we're saying. If you could take the Earth and hollow it out and fill it full of blueberries, there would be as many blueberries in the Earth as atoms in a grapefruit.
That's right. So how big's the atom? Well, that's really, 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 really small.
Does that kind of freak you out? Yeah, me too.
Do you know what? It gets even more crazy. Let's now look inside of each atom.
So now we're going to dig inside the blueberries, the atoms.
It's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus.
You guys know this, right? Nucleus in the middle of the atom. What's in the nucleus? Protons and neutrons.
It contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class.
Remember these? Guys, understand, this is so completely wrong, it couldn't be more wronger. This is actually what atoms look like. We'll talk more about that later.
You saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house.
Got it? Now our atom is the size of the house.
So imagine a ball that is as tall as a two-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium.
Okay, so think Lavelle Edwards Stadium. Got it? Now an atom is the size of Lavelle Edwards Stadium.
So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble.
Got it? So guys, if you could take an atom and if you could expand it to the size of Lavelle Edwards Stadium, so the electrons are moving around the nucleus up in the nosebleed seats of Lavelle Edwards Stadium, if that were the size of the atom, then the nucleus would be the size of a marble sitting on the 50-yard line. You ready for a crazier question? What's between the nucleus and the electrons at the edge of the stadium? Nothing. Atoms are 99.9% empty space. There's nothing between the nucleus and the electrons. There's that, imagine a marble at the 50-yard line, and then imagine these little particles running around the rim of the stadium. That stadium's functionally empty, right? So are atoms. We'll keep talking.
And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is
So they're running around the cheap seats.
like a ball the size of a football stadium with the nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit.
You guys doing okay? Because this is about to get worse. Oh yeah. So guys, here's what we now know. How big are atoms? They're small. How small are they? They are so small that if you had the number of atoms inside of a grapefruit and if you inflated the atoms to the size of blueberries, the grapefruit would become the size of the Earth. So there are as many atoms in a grapefruit as there would be blueberries inside the Earth. Then if you can tunnel inside that blueberry and make that blueberry, that atom, the size of Lavelle Edwards Stadium, how big's the nucleus? A marble, and the electrons are in the cheap seats, and what's in between? Nothing. Keep going.
Okay, one more thing.
Why the gorilla? I got nothing. Although I do like the apron, it's a nice touch.
If I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, and now there is some amount of mass in the electrons, but most of it is in the nucleus, how dense is the nucleus?
Okay, so now what we're saying is this. Most of the mass of an atom is in the nucleus. We'll talk more about this in a minute and we'll give it a number. But most of the mass of the atoms in the nucleus. So now guys, think about the last unit that you learned. Ready? How big is the nucleus? What'd you just learn? How big is the nucleus? Really small. But most of the mass is inside the nucleus. So small is volume, mass is mass. What do we call mass divided by volume? Density. So we're now going to talk about the density of the nucleus. So if a nucleus is really small but contains all the mass of the atom, what must be true of the density of the nucleus? It's ridiculously high. So now the question is, how high is it? Check this out.
Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed.
Got it? So if you had a meter cubed of nuclei, it would weigh 4.7 times 10 to the 17th kilograms. Get it? Yeah, me neither. So watch what he does.
But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet.
Got it? Yeah, me neither. So let's make this practical. But guys, before we do, this is a cubic foot. Yes, I made it myself. This is a cardboard box that is a foot by a foot by a foot. So this is a cubic foot. So if we had a cubic foot of nuclei, what would it weigh? Well, here we go.
Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot.
See? I followed directions.
And let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus?
Got it? Okay, so here's the question. If we wanted to make the matter inside this box as dense as the nucleus of an atom, what would we have to put in the box? And he's going to talk about this relative to cars. So guys, imagine shoving a car inside this box. That's going to be hard. That's going to be pretty dense, right? Well, we're not even close. Here it comes.
Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number.
Guys, here's the trick. If you want to make the matter inside this box as dense as the nucleus of an atom, you have got to put 6.2 billion cars inside this box. And when you jam 6.2 billion cars inside this box, the matter that is inside this box is now as dense as the nucleus of an atom. But remember, what we're talking about there is the marble in the middle of Lavelle Edwards Stadium, that if we crunch it down, there's that many blueberries inside the earth. Let's try. Yeah, 2,000, correct, exactly. So that's what, so yeah, because if on average, that's how they did the math. If they're saying that a car weighs 2,000 pounds, would give you the mass of a cubic foot of nuclei. Yeah. Oh, you're right. Oh, sorry, Cam. 2 tons is 4,000 pounds. So multiply by 4. All right. So guys, let's keep going.
People in the earth. So if everyone on the earth owned their own car, and they don't, and we put all of those cars into your box, that would be about the density of a nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, it would have the density of 1 nucleus. Okay, let's review. The atom is really, really, really small.
You sold on this? How big is the atom? Really, really, really so small that if you could take the atoms in a grapefruit, blow them up to the size of a blueberry, the grapefruit would expand to the size of the earth. Okay, that gives you a sense of how small they are.
Think atoms in a grapefruit, like blueberries in the earth. The nucleus is crazy small. Now look inside the blueberry and blow it up to the size of a football stadium.
So when we do that, how big is the nucleus? The size of a marble. And where are the electrons? Cheap seats. And what's in between? Nothing.
And now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space. That's weird. The nucleus has a crazy high density. Think of putting all those cars in your 1-foot box.
Yeah?
I think I'm tired.
All right, so guys, here's what we know. We now know two things. We know where atoms came from, and now we're getting a sense of how ridiculously small and complex they are. Atoms are amazingly small. They have a nucleus that's amazingly smaller, and they're mostly empty space. You starting to embrace these realities? Because now, guys, this is about to get really practical. The last thing that we're going to talk about today, which is going to require you creating this table, is what are atoms made of? So guys, we're about to talk about subatomic particles. You want to make this table as wide as your page, and you want to make each of the horizontal rows 2 lines tall. I'll give you a second to scratch it down, and then guys, we're going to flesh this out. And this will require that you have your periodic tables. Where'd my coffee cup go? Oh, there it is. You guys all caught up? You good? Yeah? All right. So, guys, this is where this is about to become practical. This is going to take us about 7 minutes. And what we're going to do is we are going to identify not only what are atoms made of, but we're also going to have the conversation about how many protons, neutrons, and electrons are in these atoms, which is going to be the end of our day. So guys, before we can do that, we need to talk about what those 3 particles are. So these are what we call the 3 subatomic particles: protons, neutrons, and electrons. Now guys, I asked you earlier in the day, what's in the nucleus? And many of you said protons and neutrons. Some of you were thinking to yourself, how does everybody else seem to know that? It's probably stuff you talked about in 7th and 8th grade physical science classes. But guys, the protons and the neutrons are in the nucleus. Therefore, we give them a name, and it's going to come in right here. Those are what are called the nucleons. Given where they hang out, that probably makes sense. Okay, so now guys, what we're going to do is we are going to work from left to right. And we are going to talk about the abbreviations for these particles, their masses, and then their charges. These are all things you're going to need to understand to move forward. But guys, make sure you're writing these down carefully. For example, the abbreviation of a proton is capital P positive, and the positive is superscripted on the right. Now guys, what you're going to find out is the way that we write the abbreviation tells us some things. I'm guessing you probably know the first one. What does the positive mean? The charge is positive. We'll talk in a minute. But guys, what does the fact that we abbreviate this with a capital P mean? It means that it's massive. The capitalization of the P tells us that it's massive, because remember, we learned that all the mass of an atom is in the nucleus. That's where the protons and neutrons are. So guys, protons are very massive. So then the question is, how massive are they? Well, in grams, they're this: 1.67 times 10 to the negative 24th grams. Guys, in the subatomic world, that's a dump truck. That is like, holy smokes, very, very massive. But here's the thing that's weird. Don't write this down, but watch right here. Guys, this is that number written out. That is the mass of a proton in grams. That's this number. Written out, 1.67 times 10 to the negative 24th is that. So understand, this is a ton of mass when you're as small as a proton, right? We talked about the cars and the box and the foot. Guys, that's a ton of mass when you're really small. But here's the problem. This number is a pain in the butt to write down, right? So here's what some smart scientists did. They said, if we need to know the mass of a proton, and we do, why don't we figure out another unit of mass that makes this easier? So here's what they did. They said, we're going to create another unit of mass called the AMU, or atomic mass unit. You may want to write that above this. AMU stands for atomic mass unit. And because these people are smart, here's what they said. Let's make an atomic mass unit equal to 1.67 times 10 to the negative 24th grams. See what that does for us? What's the mass of a proton in AMUs? 1. Aha! That's easier. And now, guys, I think you already know the charge. We sort of discussed... Oh, go ahead, Seal. Oh, yeah. Yeah, I can wait for you. Go ahead. So guys, what's the charge of a proton? +1. It's not just positive, it's +1. That's going to be important in a minute. You guys all caught up? Okay, so now let's do the center column, or the center row, and tell me what you now know from the abbreviation about a neutron. So it's capital N0. It's massive. How do you know? It's capitalized. And what does the 0 tell you? It's charge. It is a neutral-tron. It has no charge. So let's flesh this out. Guys, this is pretty slick. Ready? What is the mass of a neutron in grams? The same as a proton. So guess what it is in AMUs? Still 1. And then, guys, what's the charge? 0. Now check this one out. Now let's take a look at the electron, and you're going to learn a lot just by seeing this. Hey. Yeah. Like what kind? Can I bring it to you a second? I have tons. Yeah. Yeah, for sure. Yeah. So guys, what did you just learn about the electron by writing this down? Be careful with small, because that's volume. What did we learn about electrons? Not very massive. Its mass is very low. And the little negative sign, its charge. So guys, the question then becomes, how small is the mass of an electron? And the answer is this. 9.11 times 10 to the negative 28th. Now guys, because some of you are not comfortable with scientific notation, let's talk. If you really want to understand how small the mass of an electron is, the thing to do is look at the exponents. And guys, the difference between the proton, neutron, and electron is 4 exponents. That means a difference in mass of 10,000. 10, 100,000, 10,000. So electrons are about 10,000 times lighter than protons or neutrons. So check out what we do. If an electron is about 10,000 times lighter than a proton or neutron, what is its mass going to be in AMUs? About a 10,000th of an AMU. That's basically 0. So guys, we call it 0. We say that the mass of an electron is 0. Understand that it's not. It does have mass, but it's so small, it's a rounding error. We count it as 0. And now, guys, what else do you know about the electron to round out the table? It's negative charge, but it's not just negative, it's -1. Why is that important? You'll see in a second. Go ahead. Beautiful question. Guys, the question on the table is, if these things are too small to see, how do we know their masses? I'm not going to answer the question. The reason I'm not going to answer the question is because I'll give you extra credit for it on Thursday if you want to look it up. Guys, I've had people, because of their first test scores, ask me about extra credit. Can we do extra credit in this class? And the answer is sometimes. It's never because you want it. It's because I have the opportunity to give you something meaningful to do, which means extra credit will never be cookies. But on Thursday, I'll tell you about the assignment. It'll be due the day of the test. And functionally, the assignment is figure out how they weigh atoms. And it's fascinating. It's really cool. So if you want to look that up and write a little paper on it, I'll give you extra credit for it. Okay. So guys, you good with the ideas? So why are these specific numbers important? Well, guys, write this down with me. What do protons and neutrons have in common? Not only are they in the nucleus, but they are the guys that carry mass. But it doesn't stop there. Because of these three particles, while the protons and neutrons carry mass, the protons and electrons carry charge. And not only do they carry charge, their charges are equal and opposite. That's why the ones are important. What you're going to find out is that the charge of a proton is perfectly canceled by the charge of an electron. And why do we care about this? It's about to come up right here. The reason we care is because atoms don't have a charge. The charged atoms don't have charges. Here, I'm going to move this up so you can see it a little better. That'll be better. Oh, now I got to go through all those animations. Poop. Hold on. So, guys, the idea here then is that atoms have no charge. So what would have to be true in an atom for the atom to have no charge if it's a bunch of positive protons and negative electrons? Got to be the same number. The number of protons in an atom equals the number of electrons in an atom, and therefore their charges cancel out, and we end up with no charge. How are we doing? Guys good? All right. So now, guys, what we've got to do, and we're just about to the end of this, we've got to figure out how many protons, neutrons, and electrons are in an atom. And guys, all of that information is on your periodic table. You've just got to figure out how to find that information. So guys, don't grab your periodic tables yet. Let me orient you to this, and then we'll play with it. So guys, this is the information you need to know. And this should be in your notes. So guys, the first number that you need is what is called the atomic number, and it is abbreviated Z. So the atomic number is the number of protons in the nucleus. But then, of course, we know it's also the number of electrons in orbit because protons and electrons are the same. And the other number that you need to know is the atomic mass. It is abbreviated A. And the atomic mass is the number of protons and neutrons in the nucleus. And guys, with those two bits of information, you can actually figure out what is every atom on the periodic table made of. But the first thing you need to know before we can get into this is you've got to understand we represent this in one of two ways. Sometimes you'll see it like this. You'll see the abbreviation of the element, like carbon. And then the atomic mass will be on the top, and the atomic number will be on the bottom. At other times you'll see it like this, where we write out the name of the atom, and then there's a dash. It's not a negative sign, it's a dash. And then the number 12, which is the atomic mass. So this is the way we represent it. What we really need to talk about is where do we get the numbers. This is where you grab your periodic tables. So guys, just get used to doing this. In the bottom left-hand corner of your periodic table is the secret decoder key. You'll notice that it's based on zinc. Don't know why they chose zinc. But if you look in the bottom left-hand corner, what you need to do is find atomic number and atomic mass, which I believe they call atomic weight. Same thing. So guys, where is the atomic number in these boxes? Top left. And what color is it? It's blue. And then the atomic weight or mass is in the upper right, and it's in red. So now let's review. What does the atomic number tell you about the atom? Protons. What does the atomic weight tell you? Protons and neutrons. And what are the units for those numbers? AMUs. So guys, check this out, because if you understand what's going on, you're not going to like this. You ready? Take, for example, let's go to carbon. Find carbon on your periodic table. What is the atomic number of carbon? 6. So what does that tell you about carbon atoms? 6 protons in the nucleus. Now look at the atomic weight of carbon. And guys, what is the atomic weight of carbon in AMUs? 12.01. Is it 1? Okay. So guys, do you see the problem? What does atomic weight represent? The number of protons and the number of neutrons. So check this out. What's the mass of a proton? 1. What's the mass of a neutron? 1. What kind of numbers do you get when you add up a bunch of ones? Whole numbers. So why is that not a whole number? We're going to talk on Thursday. It's not the mass of the electrons. Guys, we are going to answer that question on Thursday. For now, here's what we're going to do. We are going to round. We're not going to talk about it. Guys, we are going to round these numbers to whole numbers. So we're going to say the mass of carbon is 12, even though we know that it's 12.011. We'll talk about the decimal on Thursday. You okay? Okay, so guys, do this with me then, and please don't write this down. Check this out. I think you can answer these questions now. So guys, how do we know how many protons are in an atom? Look at carbon. How many protons are in carbon? 6. The atomic number. The atomic number Z tells you the number of protons. Now guys, what about this? How do we know how many electrons are in an atom? It's the same. The protons and electrons are the same so that the charge balances. So now guys, you ready for the tricky question? How many neutrons are in an atom? Good. It's just like the thing that we did in lab where we said, here's the mass of the dish plus the salt. Here's the mass of the dish. Subtract and it gives you the mass of the salt. But guys, do this. The atomic mass tells you protons and neutrons. What does the atomic number tell you? Protons. Subtract the two and what are you left with? Neutrons. So guys, the number of neutrons in an atom is the atomic mass minus the atomic number. So with that in mind, write this down with me. Draw yourself a big circle and a little circle. Make the big circle about 3 inches across. So guys, check out what you just drew. You just drew an atom. What does the small circle represent? The nucleus. What does the big circle represent? The electrons. Is this to scale? No, because if it were to scale, how big would the nucleus be? Well, the size of a marble. So guys, if we could take this circle and squeeze it down to the size of a marble, how big would this circle need to be? Lavelle Edwards Stadium. Let's not draw this to scale, shall we? But guys, do you understand the idea? If the nucleus is the size of a marble, the big circle is the size of a football stadium. It's not to scale. But here's what we are going to do. We're going to fill this in for an element like potassium. So guys, find potassium on your periodic table. It's the 4th one down in the left-hand column. Its abbreviation is K. And here's what we're going to do. We're going to figure out how many protons, neutrons, and electrons are in a potassium atom. So guys, let's do protons first. How many protons are in potassium? 19. How do you know? It's the atomic number. So guys, there's 19 protons in the nucleus of a potassium atom. So if there's 19 protons in the nucleus, what does there also have to be 19 of? Electrons in orbit, because the protons and the electrons balance each other out. Now, guys, we've got to figure out how many neutrons are in the nucleus. So we come over and look at potassium, and potassium has a mass of 39.09 something or other, which rounds to 39. So, guys, the idea is this. If the entire nucleus weighs 39 and it contains 9 protons, how many neutrons does it have to have? 20. Subtract. Because don't 19 protons plus 20 neutrons add up to 39, which is the mass of the atom? And that's how the math works. Do you get the idea? Now, guys, here's the trick. We can do this for every atom on the periodic table. But trying to draw these circles for every atom on the periodic table is going to fill pages and pages and pages in your notebook. So we're going to do this instead. Don't write this down. This is the way that we are going to do this. We're going to do it in table form. So let's do the first couple together to make sure that you understand how this goes. So guys, looking at the periodic table, find helium. No, just this isn't, wait, or is it? Oh my gosh, this is your homework. P.S., this is your homework. Let's do the first couple together. How did you guys know that? You all started going to your homework. You guys are like students. No, I know, it's true. Don't tell anyone. Does anyone else need one? They're going cheap. Okay, guys, so you guys apparently understand this and I missed it. This is your homework, so let's do the first couple together. So what you're trying to do is you're trying to fill in the boxes. So we take a look at helium. Helium, guys, is element number 2 with a mass, oops, let's make this stand out, is element number 2 with a mass of 4. So if it is element number 2, atomic number 2, how many protons does it have? 2. Now, once we know protons, we also know what? Electrons. Then, guys, the next thing that we need to do is neutrons, and protons and neutrons are always the same. Huh? Protons and neutrons are always the same? No. Protons and neutrons are not the same, but to find the number of neutrons, it's atomic mass minus atomic number. 4 minus 2 is 2. Now, guys, you'll notice the second example, there ain't much there. But there doesn't have to be, because what do they give us? The atomic number, which tells us that this is element 12, which tells us that this is magnesium. Now, guys, capitalization doesn't matter, but spelling does. The M could or doesn't need to be capitalized. But, guys, when you write the abbreviation, if you don't have big M, little g, it's wrong. It's got to be capital first, lowercase second. If your handwriting is as bad as mine, fix it. If you put little smiley faces and stuff in your eyes and curly cues, and knock it off. It's big and then little. Okay. Now, guys, magnesium is element number 12. Now we need to know its mass. Does that, yeah, it rounds to 24. So, guys, what that tells us then is the atomic number is the number of protons. That's equal to the number of electrons. And you just keep going. How you doing? So, guys, I still think you may get your homework done. You've got 10 minutes. You'll notice that this homework is just single-sided. We're just completing this table. I will post the answers up on the wall. Let's get this thing knocked out. We'll fine-tune this on Thursday, talk about a couple more things, lab on Monday, test next Wednesday. You guys good to go? Go get 'em.